This is a chain fountain. It's an ordinary ball chain flowing out of a container and onto the floor under its own weight. What surprises most people is that the chain doesn't just slide over the edge of the container. Instead, it leaps into the air like a fountain, rising well above the edge of the container before it falls back down. This effect was first brought to the public's attention in a 2013 YouTube video by Steve Mould. It's often called the Mould effect. I saw Steve's video a couple of years ago in 2019 and was instantly intrigued. I guessed, like many people do, that the effect is caused by inertia in the chain. In other words, the upward moving portion of the chain is unable to turn around quickly due to its own inertia, so it rises above the edge of the container and gradually turns over before falling downward. That explanation isn't correct. To my knowledge, the first serious attempt to explain the chain fountain was given by John Biggins and Warner and published in the Proceedings of the Royal Society. A more complete analysis was given by Biggins in 2014 in his paper called Growth and Shape of a Chain Fountain. After learning about these papers, I assumed the question of how the chain leaps out of the container was resolved. But a few weeks ago, in summer of 2021, interest in the chain fountain was reignited when simultaneously Steve and Mehdi Sadaoudar released videos offering different explanations of the effect. You can find Mehdi's video on his YouTube channel, Electroboom. Steve's explanation of the chain fountain is basically the same as the one originally given by Biggins and Warner, but Mehdi and others on social media disagree with that explanation. Just carry out a YouTube search for videos on the chain fountain from around 2021 and you'll see what I'm talking about. In watching this controversy unfold, I'm reminded of some advice I heard on several occasions during my graduate school days. Advice from the famous physicist Bryce DeWitt. Professor DeWitt would observe students or faculty engaged in a long-winded debate as they argued over the details of some complex physics problem. Eventually, Professor DeWitt would interrupt and say, "Just do the damn calculation." It was his way of pointing out that you can discuss and argue and debate over and over, but at some point it's a waste of time because words can never replace an actual calculation. You'll never be sure of the answer until you just do the damn calculation. So here's my input to the chain fountain discussion. I'm going to do the damn calculation. Let me say from the outset that the results I present, I believe, are equivalent to those found in John Biggins' 2014 paper. That paper is referenced here, along with the original Biggins and Warner paper and a couple of other papers on the subject. So let's get started. For the moment, we're going to model the chain as a continuous cord or string that's thin, infinitesimally thin, and flexible, and cannot be compressed or extended, incompressible, and inextensible. So here's the cord, and I'll draw it with some thickness just to make it look better. And we're going to lay the cord on the table, and we're going to take a marker and mark along the cord distances that we call S. So this is, say, S equals 0. Here's a mark, S equals 1, 2, 3, and these can be centimeters or whatever units you like, and so forth. Now, in order to specify the motion of the chain, we need to tell the location of each point along the chain at each time. So if here are my Cartesian coordinate axes, let's call this the x direction, we'll call the y direction up, and the z direction. Then we need to specify the x, y, z values. We'll group those together as a vector, x vector, for each value of t and each value of s. So our goal is to compute this position vector, x vector, for each point on the chain s for each value of time t. Now the derivative of this position vector with respect to s, I'm going to call that x vector prime, so that's just shorthand notation for the partial derivative of x with respect to s, and it's a partial derivative, so we're holding t fixed. This, it turns out, is the unit tangent to the chain. The unit tangent vector. It's not too difficult to show this. Let me draw another picture. Here are the x, y, and z axes. And now I'm going to draw a short segment of the chain from parameter value s to a nearby value s plus delta s. So this is parameter value, some generic value s, and this is a nearby value s plus delta s, where delta s is small. Now the position vector of this end of that chain segment is, of course, x of t and s. And the position vector for this end of the segment is x of t and s plus delta s. The difference between these two position vectors, let's just call that delta x. So delta x is equal to x at time t and parameter value s plus delta s minus x at t and s. And you can see from this picture that this is tangent to the chain. And of course we can divide delta x by delta s. And the vector will still be tangent to the chain. And in the limit as delta s goes to 0, this is just the derivative of x with respect to s, which we call x prime. So x vector prime is tangent to the chain, but it's also unit normalized. It's a unit vector. And we can see this by just computing the dot product of x vector prime with itself. From this definition, this is delta x vector dot delta x vector divided by delta s squared. But delta x vector dot product with itself is just the length of this vector. And remember, the parameter s is measuring distance along the chain, so the length of this segment of chain is just delta s. So this is equal to delta s squared divided by delta s squared, which is 1. Now let's apply Newton's second law to this segment of chain. So once again, here's the segment of chain from s to s plus delta s. Let me draw some of the chain on each side of the segment. The forces acting on this segment are the gravitational force, pulling it down, and the tension in the chain. So the tension means this part of the chain pulls on the segment with a force like this, and this part of the chain pulls on the segment with a force like this. Now these are all vectors, so remember the up direction is the y direction, so this gravitational force is minus mg times y hat. Y hat is the unit vector in the up direction, and m is the mass of this segment. Now what about this tension force? Well, the magnitude is just the tension in the chain at this point, and the direction is tangent to the segment, so that's x vector prime. That's the unit vector that's tangent to the chain. So this is the force vector of this part of the chain acting on the segment, and it's to be evaluated at this location, s plus delta s. And likewise, this force vector is minus t times x vector evaluated at s. And the reason for the minus sign is because, remember, x vector prime is the unit vector pointing along the chain, but it's pointing in the direction of increasing s, so it's pointing in the opposite direction to this force vector. And now we can apply Newton's second law. The sum of these forces is t times x vector prime at s plus delta s minus t times x vector prime at s minus mg times y hat, and that equals the mass of the segment times the acceleration. The acceleration is just the second time derivative of the position vector. Strictly speaking, this should be evaluated at the center of mass of the segment, but it doesn't matter because I'm about to take the limit as delta s goes to 0, so we'll just let this be evaluated at t and s. Now the mass of the segment can be written as the mass per unit length, which we'll call lambda, times the length of the segment, which is delta s. So here we're denoting by lambda the mass per unit length. Then this expression, inserting this for the mass and dividing through by delta s, we have t times x vector prime at s plus delta s minus t times x vector prime at s divided by delta s minus lambda g times y hat equals lambda times the second time derivative of x, which we'll just denote by x double dot. So I'm using the notation where dots denote a time derivative. In the limit as delta s goes to 0, this expression just gives the derivative with respect to s of the quantity in parentheses here. So this is partial with respect to s of t times x vector prime. And I'll denote that for simplicity as just t times x vector prime and this whole quantity primed. This gives us the following partial differential equation that governs the motion of the chain. It's the tension T times x vector prime, all of that primed, minus lambda g times y hat equals lambda times x double dot, where the primes denote derivatives with respect to the parameter s, the dots denote derivatives with respect to time, and remember we also have the side condition that x vector prime is a unit vector. What we'd like to do is find stationary solutions of these equations. What I mean by stationary is that the shape of the chain is constant in time. But the chain can be moving with speed v along its own length. Let's draw another picture. Here's the chain, and this is the position vector for the location S on the chain at some time t, and let's say the position vector at the same time for some parameter value s plus delta s is here. By a stationary solution, I mean this point S on the chain is going to move with speed v and at some later time arrive at this same point with this same position vector. So this is equal to x of t plus delta t and the parameter value s, where delta t is the amount of time it takes the chain to move from here to here, which is a distance of delta s. In other words, delta s over delta t is just equal to the speed of the chain v. And we'll assume that the speed is a constant in time. This is a stationary solution. It also has to be constant in s because otherwise the chain would be bunching up or stretching out in some locations as it moves. And remember, the chain is inextensible and incompressible. Putting this together, we have x of t plus delta t and s is equal to x of t and s plus v times delta t. And now let's expand both sides in a series in delta t for delta t small. This is x of t and s plus partial x with respect to t times delta t plus higher order terms. And on the right hand side we have x of t and s plus partial x with respect to s times v times delta t and so forth. Now taking the limit as delta t goes to 0 and dropping these higher order terms, of course these terms cancel. This shows us that partial x with respect to t is equal to v times partial x with respect to s. Or in other words, using our shorthand notation, this is x dot equals v times x prime. We can differentiate this equation with respect to t, so on the left-hand side we have x double dot, and on the right-hand side we have x prime dot, but x dot is v times x prime, so this is just v squared times x double prime. And now we can use this result to replace the acceleration in Newton's second law, and we have the following result. T times x vector prime quantity prime minus lambda g times y hat equals lambda v squared times x double prime, where x prime is a unit vector. These equations describe a stationary solution for the chain. That consists of ordinary differential equations, ODEs, for the shape of the chain, for x as a function of s. Now notice this equation can be easily integrated with respect to s. The first term here is just t times x vector prime. This next term is these are just a bunch of constants, so the integral is minus lambda g y hat times s. This term is lambda v squared times x vector prime, and then we need to add some constants of integration, and I'll add them in the form minus lambda g times k vector, where k is a vector of constants. Let's rearrange this equation. We have t, this term, minus lambda v squared all times x vector prime equals lambda g times y hat s minus k. Now let's square this equation, that is, take the dot product of the left-hand side with itself and set that equal to the dot product of the right-hand side with itself. So this is equal to lambda squared g squared times, this is just the magnitude of y hat s minus k squared. And now recall x vector prime is a unit vector, so this factor is just equal to 1. And what we find then is that t minus lambda v squared, taking the square root of this, is either plus or minus lambda squared, not squared, lambda times g times the magnitude of y hat s minus k. Now instead of writing plus minus here, I'm going to insert a factor of epsilon, where epsilon is either equal to plus 1 or minus 1. Now let's use this result in this equation. So the left-hand side becomes epsilon lambda g times the magnitude of y hat s minus k times x vector prime equals lambda g times the vector y hat s minus k vector. So now the lambda g's cancel, and we can solve this for x vector prime. X vector prime is just multiplying through by epsilon, which is either plus or minus 1. This is epsilon times y hat s minus k divided by the magnitude of y hat s minus k. What I'd like to do now is simplify the calculation a little bit by specializing to just 2 dimensions. In other words, we'll assume that the motion takes place in the xy plane. then the x component of this equation becomes x prime equals epsilon times, well, the x component of y hat is 0, so this is just minus the x component of the vector k, I'll call that k sub x, divided by the magnitude of this vector, that's the square root of the x component, which is minus kx squared, plus the y component, which is s minus ky squared. And the y component of this equation is very similar. It's just the numerator here is, instead of minus kx, it's s minus ky. So we have y prime equals epsilon times s minus ky divided by the square root of, we'll just drop that minus sign, kx squared plus s minus ky squared. Now let's do a little side calculation. Let's differentiate this with respect to s. And what we find then is y double prime equals, after some simplification, this is epsilon times k sub x squared divided by this square root term cubed. So notice all of this is positive. So the sign of y double prime is determined by the sign of epsilon, whether epsilon is plus or minus 1. Since we want to look for solutions that are concave down, like the chain fountain, we're going to choose epsilon to be minus 1. So our results for x prime and y prime become the following. We have x prime equals k sub x divided by the square root of kx squared plus ky minus s quantity squared, and y prime is k sub y minus s divided by the square root of kx squared plus ky minus s squared. These equations describe the shape of the chain fountain as a steady state or stationary solution of the equations of motion for a moving chain or cord. Let me draw a picture. Here are the xy axes, and here's the chain, and it's moving in this direction. And I'll assume that the parameter s that parameterizes the length of the chain is increasing in this direction. So in other words, I'm going to assume that x prime is positive, and that tells us that this constant k sub x is positive. Now let's integrate these equations with respect to s. The result is x as a function of s is equal to the constant k sub x times natural log of square root of kx squared plus ky minus s quantity squared minus ky plus s divided by square root of kx squared plus ky squared minus ky. And for y we have a constant that I'll call h plus square root of kx squared plus ky squared minus the square root of kx squared plus ky minus s squared. Now in integrating those equations, I chose the constants of integration such that x at s equals 0 is 0, and y at s equals 0 equals the constant h. So in other words, in this picture, I'm assuming that this point right here is y equals h and x equals 0. Now if you'll recall, we earlier had an expression for the tension as a function of s right here. And specializing to epsilon equal minus 1 and to 2 dimensions, we can write this explicitly as T of s equals lambda v squared minus lambda g times the square root of kx squared plus ky minus s squared. And now notice the s dependence in y and the s dependence in t are both through this square root factor, so we can replace this square root with y minus these constants. And that gives us a nice expression for t as a function of y, the height. It's lambda times g times y minus h plus lambda v squared minus lambda g times the square root of kx squared plus ky squared. We've now managed to find the general solution for the shape of the chain. And by the way, this shape is called a catenary. It's written here in parameterized form with the parameter s. But the solution is incomplete because we don't yet know what these constants are, the kx and the ky. We also don't know what the constant speed v is. These constants all depend on the details of the chain. And as we'll see, the details of the chain determine how the chain is picked up from the container and how it's dropped off at the floor. Let me draw a picture once again. Here's the y-axis and here's the x-axis. This is the bottom of the container at a height h. The container C at y equals h. And this is the floor, F, at a height y equals 0. And the chain, of course, flows like this. Let's first take a close look at how the chain is pulled out of the container. So here's the bottom of the container, and here are some of the beads in the bead chain. And here's the chain itself coming out of the container. Let's let L denote the separation between beads. And remember, this is now flowing out with some speed v. So the speed v is equal to L over delta t, where delta t is the time it takes this bead to move through a distance L. It's also the time it takes one bead to be picked up out of the container before the next bead has to be picked up. Now, when a bead is picked up, it starts from rest, and it has to be accelerated up to a speed v in a time delta t. So applying Newton's second law, we have the force on the bead equals the mass times acceleration. Now the mass of the bead is just the mass per unit length times the length spanned by one bead, and the acceleration is the final speed minus the initial speed minus divided by delta t. So this is lambda times L times v divided by delta t is L over v. So you see the L's cancel, and we have, this is just lambda times v squared. So the total force that accelerates the bead out of the container must equal lambda times v squared. So what are the forces acting on a bead as it accelerates up to speed v? Well, we have the tension in the chain, and I'll call that T sub c for the tension at the location of the container. There's the weight of the bead, minus mg, and we also need to consider the possibility that there's a force that the container exerts on the bead. I'll denote that by F sub c. So here's a picture of the bottom of the container with the beads, and the bead is being accelerated up to speed v, and the forces acting are the tension at the location of the container. We also have a force from the container itself, and we have the gravitational force, mg. Now this force from the container, it could be due to lots of factors. It could be buoyancy forces, frictional forces, and so on. And we'll talk about that more later. For now, let's notice that this gravitational force is going to be very small compared to these other forces. Remember, m is the mass per unit length times the length. And the length here is very small. In fact, in the limit as L goes to 0, it's vanishingly small. So we'll ignore this gravitational force, and we'll write Newton's second law as just the force of tension in the chain at the location of the container plus the force that the container itself exerts equals lambda v squared. And now let's carry out the same analysis at the floor. So here's the floor. There are beads piling up on the floor as the chain falls. And now the forces on a bead are, first of all, the tension in the chain at the level of the floor, so I'll call that T sub F. There's also forces that the floor might exert on the bead, and we have then as well gravitational force. And these forces combined have to accelerate the bead. They have to bring the bead's speed down from v down to 0 in a time of delta t. And the acceleration is upward. It's the final velocity minus the initial velocity divided by delta t, which is equal to v squared over L. And the mass, again, is lambda times L. So multiplying these, the L's cancel. And what we have then is the total force, the force of tension, plus the force of the floor itself. And we'll ignore the gravitational force since it's very small compared to these other forces. This equals lambda times v squared. And now we can use our previous result for the tension right here to evaluate the tension at the level of the container, that's setting y equal to h, and at the level of the floor, that's just setting y equal to 0. And then these equations become Tc is lambda v squared minus lambda g times square root of kx squared plus ky squared. That's the tension at the level of the container, plus the force that the container exerts equals lambda v squared. And for the floor, we have minus lambda gh minus lambda v squared minus, that's rather plus lambda v squared, minus lambda g times square root of kx squared plus ky squared plus ff, the force of the floor, equals lambda v squared. Now in these equations, the lambda v squareds cancel, and what we're left with then is the force that the container exerts equals lambda g times square root of kx squared plus ky squared, and that the force that the floor must exert is lambda g times square root of kx squared plus ky squared plus lambda gh. Now one thing you should notice about these results is that the force that the container exerts on the bead as the bead is accelerating up out of the container, that force must be greater than 0 unless kx and ky are both equal to 0. So Fc is always greater than 0 unless kx equals ky equals 0. But if you go back and examine the solutions for x as a function of s and y as a function of s, you'll see that in the limit as these go to 0, x of s is just 0, and y of s is h minus s. So the chain, in this case, just falls straight down. So that's not a chain fountain. So in order to have a chain fountain where the chain actually rises up above the level of the bottom of the container and then back down, we need to have Fc greater than 0. So at least one of these constants has to be non-zero. So why is Fc greater than 0 for a bead chain? Biggins and Warner had the insight that a bead chain isn't infinitely flexible. So here's some beads, and they're connected together by little wires. Now if we try to lift this end bead upward, what happens is it pulls on this bead next to it. So this group of two beads then rotates as a unit upward. So counterclockwise in this picture. This suggests that we model the bead chain as a set of stiff links. Now let's look at the way a link is lifted out of the bottom of the container. So this is the tension force, the rest of the chain pulling on this link at the level of the container. We also have gravitational force pulling it down at the center of mass. And over at this end that's still resting on the surface of the container, we have a force F sub c. And now we write down Newton's second law. First, the sum of the forces, Tc plus Fc minus mg equals the mass of this link times the acceleration. Let's call that y double dot, where y is the height of the center of mass. Y is the center of mass coordinate for the link. We can also write down Newton's second law in angular form. So here's the table. Let's say the link makes an angle theta with respect to the table. So the torque about the center of mass due to this force, Tc, is T sub c times this distance, which is L over 2, if L is the length of the link, times cosine of theta. And acting in the other direction, we have the torque F sub c times L over 2 cosine theta. That's the sum of the torques about the center of mass equals the moment of inertia about the center of mass times the angular acceleration, the second time derivative of this angle. As the right end of the link is being pulled upward by the tension, the left end of the link will slide along the surface of the container until the link is vertical. So during that time, the y coordinate of the center of mass will equal L over 2 times sine of theta. Now we could try to solve these equations, but we'd probably have to do it numerically. So instead, let's look at the beginning of the pickup process when this angle theta is very small. So in the beginning, when theta is small, we have cosine theta is approximately 1, and from this equation, y is approximately L over 2 times theta. And our equations here become Tc plus Fc minus mg equals m times y double dot. And this equation becomes Tc times L over 2, cosine theta is about 1, minus Fc times L over 2 equals I times theta double dot, but theta double dot is 2 over L times y double dot. Let's simplify these equations as Tc plus Fc equals my double dot plus mg, and Tc minus Fc equals 4 multiplying through by 2 over L, we have 4I over L squared times y double dot. And now we can subtract these two equations from one another to eliminate Tc. What we obtain is 2Fc equals m minus 4I over L squared times y double dot plus mg. Now the center of mass of the link must accelerate from speed 0 to speed v in a time delta t, so y double dot equals final velocity minus initial velocity over delta t, where delta t is given by v equals L, the length of a link, divided by delta t. So y double dot is equal to v squared over L. Now, as we've done before, we're going to ignore this term mg. After all, if you look at the acceleration y double dot, and the limit as L becomes small, y double dot is very large, much larger than the acceleration g due to gravity. So ignoring this term, we have the force that the container exerts on the bead chain is 1/2 m minus 4I over L squared times v squared over L. For example, for a link with uniform density, the moment of inertia will be 1/12 the mass of the link times L squared. So Fc in this case is 1/2, factor out m, we have m times 1 minus 4 over 12 is 1/3 times v squared over L. And the factor in parenthesis is 2/3 times 1/2 is 1/3 times m v squared over L. And remember, the mass is the mass per unit length times L, so that's equal to 1/3 lambda times v squared. Now, we don't really expect this result to be correct. Keep in mind that we not only oversimplified the bead chain as a set of links, but we also solved the pickup equations only in the limit of small angle. So I'm going to follow Biggins and Warner and write Fc as some constant alpha times lambda v squared, where alpha could be determined by a more complete calculation or an experiment. Now, when the beads hit the floor, recall that we earlier derived the expression that the tension at floor level plus the force that the floor exerts on the chain is equal to lambda v squared. So if the tension at floor level is 0, that means that the force that the floor exerts to decelerate the beads as they hit the floor is just lambda times v squared. However, it can turn out that this tension doesn't have to be 0. If we once again model the bead chain as a set of links, here's a link just as it's beginning to hit the floor, and it's hitting the floor at an angle. So when it does so, it rotates, and this top end, which is linked to the next link or the next bead, it can pull down on that the rest of the chain. And so there can be a non-zero tension here as the links or the beads hit the floor. So once again, following Biggins and Warner, I'm going to write this force that the floor exerts as not quite lambda v squared, but 1 minus some constant times lambda v squared. So let's continue the analysis assuming that alpha and beta are known. In fact, Biggins, in his 2014 paper, states that alpha equals 0.12 and beta equals 0.11 are pretty good fits to the experimental data. Now, if you'll recall, earlier in the calculation we derived the results Fc equals lambda g times square root of kx squared plus ky squared, and F floor equals lambda g square root of kx squared plus ky squared plus lambda gh. And now we know this is equal to alpha lambda v squared, and FF is equal to 1 minus beta times lambda v squared. And now we can use these results to solve for two of the three unknown constants, the three constants being kx, ky, and v. So let's subtract this first equation from the second. These terms cancel, and we have lambda g h equals 1 minus alpha minus beta times lambda v squared. Now the lambdas cancel, and we can solve for the speed v. It's equal to g times h divided by 1 minus alpha minus beta to the 1/2 power. Now let's use this result for v in the first equation and solve for k sub x. We have lambda times g times the square root of kx squared plus ky squared equals alpha times lambda times v squared, which is g times h over 1 minus alpha minus beta. Now lambda and g cancel on each side, and we're left with kx equals plus or minus square root of alpha h over 1 minus alpha minus beta quantity squared minus ky squared. Now remember, earlier we chose to orient the chain fountain so that x prime is positive, and that implied that k sub x is positive. So I'll erase this plus minus sign and we'll just take the plus root. Now if you'll recall from earlier, we had an expression for the tension in the chain as a function of the height y. Here it is repeated, and now if we use our results for v squared and kx to simplify this, we find the following result. T as a function of y is equal to lambda g times y plus beta h divided by 1 minus alpha minus beta. And now let's turn to the equations for the shape of the chain. Here they are. And if we use our results for kx to simplify this, well, it's not really more simple, but at any rate, what we get is x of s equals square root of alpha h over 1 minus alpha minus beta squared minus ky squared times the natural log of square root of alpha h over 1 minus alpha minus beta squared minus 2ks ky times s minus, or rather plus s squared minus ky plus s divided by alpha h over 1 minus alpha minus beta minus ky. And for y of s, we have h plus alpha h over 1 minus alpha minus beta minus square root of alpha h over 1 minus alpha minus beta squared minus 2 kys plus s squared. We now have the solution reduced to a form with just one unspecified constant, namely k sub y. There's one more condition that we can impose. Let's look once again at the chain as it's lifted out of the container. So this time let's draw the chain coming out of the container at some angle that's not a right angle here. So the forces acting on the chain are the tension in the chain, and that acts tangent to the chain. We have the force that the container exerts, and I'll just go ahead and write the normal force as F sub c. This is the tangent tension. Since this chain is coming out at an angle, it's trying to drag the beads along the container, those that haven't been lifted yet. So there might also be a frictional force. But notice that these forces are acting in such a direction as to try to pull the chain back towards the vertical. And likewise, if the chain leaves at an angle like this, and we draw the forces, we have the tension, T sub c, we have the normal component of the force that the container exerts, and we have possibly a friction force. But these forces are all acting in such a way as to pull the chain back towards the vertical direction. So the extra conditions that we need to impose is that at liftoff, in other words at s equals 0, we have y prime equals 1. In other words, it lifts off in the vertical direction. Or equivalently, we can write x prime at s equals 0 equals 0. So let's impose this condition. We'll differentiate this function with respect to s and then set s equal to 0. And the result is y prime at 0 is equal to k sub y divided by alpha h divided by 1 minus alpha minus beta. And this condition says that should equal 1. So in other words, k sub y should equal alpha h over 1 minus alpha minus beta. And now using this value for k sub y in our solution for y as a function of s, this simplifies to y of s equals 1 minus beta times h divided by 1 minus alpha minus beta minus the absolute value of alpha h over 1 minus alpha minus beta minus s. And we can also use this in our expression for x as a function of s. We actually get 0 times log of something over 0, so that's 0 times infinity. In order to evaluate this, you need to take a limit as k sub y approaches this value. And if you do, you find that x as a function of s is simply 0. So let's draw a picture. Here's the x-axis, which coincides with the floor. This is the y-axis. And the bottom of the container is at a height h. The chain is lifted out of the container, rises to some maximum height, and then falls back down to the floor with 0 width. And this peak height, call it y peak, is just given when s is equal to this value. So it's equal to 1 minus beta times h over 1 minus alpha minus beta. Hopefully it's clear that this is describing an idealized stationary solution. The chain can't actually travel straight up and straight back down without running into itself. In practice, the fountain must have some finite width in order for the chain to clear the sides of the container. So this is the container, and here are the beads in the container, and the fountain coming out. Keep in mind that the chain can never actually reach a steady state, since the beads must be picked up from various places in the container. So once the fountain is established, the width can't shrink to 0 because the chain would hit the side of the container. And you'll notice in videos that the chain does, in fact, hit the side of the container from time to time. The tendency of the chain to want to shrink to a 0 width can be reduced by tilting the container. In that case, the chain still wants to leave the container at right angles to the container, but that's no longer in the vertical direction. So you can see how the calculation would go. You would replace this 1 with, say, cosine of the angle of the container, and that would change the value of ky slightly and give a solution that has a finite width. Independent of those details, we can still use our results to estimate the height of a chain fountain. From this expression for the peak, let's use alpha equals 0.12, beta equals 0.11, and let's choose a height h of, say, 2 meters. Then y peak is about 2.3 meters. In other words, the chain rises about 30 centimeters above the container. So there you have it, the dam calculation for the chain fountain. I think Bryce DeWitt would be pleased. I want to thank Steve Mould for allowing me to show clips from his videos, and I thank you for watching.